As I was saying before, I like the oxidation states method because it's quick. It may not feel quick to you yet, but you'll get good at it, okay? But when we head into electrochemistry, we're actually going to have to look at each side separately. So the oxidation side, we're going to have to look at the reduction side separately. That's why I like this next method also comes in handy. Plus, this next method will allow you to balance really complicated ones. Whereas after a certain point in time, this becomes a little crazy if you're balancing really difficult ones. Okay? You guys, I know that last little thing, I like that. I really like it. Let me write that one down. That was a good one. Hold on. What was it? S2, so thiosulfate plus iodine, yes, yielding the iodide ion plus the metabisulfate. Okay, got it. That's a good one. Next, half-reaction method. First one's called oxidation states method. This one's called the half-reaction method. This is brand new for everyone. None of you have seen this before, with the exception of Aaron because he looks this stuff up all the time, right? No. Okay. Remember, this could possibly go out to the world. Okay, so I'm going to. I had something I was going to say, but I'm choosing not to because it's going out to the world. Yeah, I know. But at least he's not trying to hold it in his eyelids. No. Go ahead, get in the position that you did in physics. He's telling me to go on. Okay, here we go. So this is the half-reaction method. Do I have to write that up here? No. Okay, this is the half-reaction method. Basically what we're going to do is split the reaction into the reduction half and the oxidation half, balance each half separately, really not a whole lot differently than what we've done in the other thing, and then add the two reactions together. It doesn't matter which one you do first, whether you do the reduction first or the oxidation first. It doesn't matter because they're all going to get ended up adding up together anyway. So, first example. This first one is going to be very, very easy, so I can teach the process. And then we'll just start bumping it up. Okay? I'm going to try something here. I do not know if it's going to work. I need to both do a video and show you the rules at the same time. I don't know if this is going to work, so give me a second. It may not work. I don't think it's going to work. If it does work, something really weird is going to be happening up here. Oh, wasn't that on? It was. I turned it on once. Okay, here we go. It's still working. There we go. There it is. There's the rules. All right, here we go. First step is exactly as it always is. I want to emphasize once again that I'm starting off with a very simple one, just so we learn the process. Here's the thing. You really, once you know that process and you, okay, there are 3 of you in here that will screw this up. I will name you, okay, because many of you, some of you, and this is a good thing, try to find easier ways to get things done. Take shortcuts. And that's not a bad thing. However, I am telling you right now, you cannot do that with this. Okay, Aaron? There are no shortcuts. I'm serious. There are no shortcuts. If you follow the steps, you can't screw it up. But if you don't follow the steps, you can screw it up. Okay, Lucas? All right. I got 2 of the 3 done. I'm not entirely sure who the 3rd one is, though. Oh, definitely. Definitely. Absolutely. I didn't even see Max isn't here. Max would definitely be one of those people to do that, okay? So anyway, here we go. What are we going to do? Find the oxidation states, find out what's oxidized, what's reduced. You already did that. Excellent. Boom, done, right? Okay. You guys pick, Jacob, you want to do the oxidation half first or the reduction half first? Oxidation, he says. Here we go. So, what oxidized? Now, notice that I came way over to the left. And the other thing that I'm going to encourage you to do is put an arrow in the middle of your paper. Because basically what we're going to do is build from the center out. May not be a big deal for this one because, again, it's a fairly simple reaction, but later on you're going to find out that we're going to take up like the entire line. Okay, so oxidation. What species oxidized? Anyone can tell me. Iron. So what we do is write only the species that were involved in oxidation. In this case, it was iron, and going from iron 2, to iron 3. Then, by the way, this is available on Canvas, both in the files and I think it might be available in the module. I can't remember, but it is definitely in the files. So balance every atom other than oxygen and hydrogen. Done. Balance oxygen by adding water. Done. Balance hydrogen by adding hydrogen ion. Done. There, this was easy. Okay? Next. Oh, balance the charge by adding electrons to the appropriate side. To the reactant or product? Product side. Add 1 electron to the product side. That equalizes the charge. Would you guys agree? Okay, next, let's do the reduction side. The species involved in the reduction are the permanganate ion and the manganese 2 ion. Okay. As it said, balance each atom other than oxygen and hydrogen. Done. Balance the oxygen by adding water to the appropriate side. We need to add 4 water to the product side. Add hydrogen ion, or balance the hydrogen by adding hydrogen ion to the appropriate side. 8 hydrogens on the reactant side. Balance the charge by adding electrons to the appropriate side. Well, we have a net plus 7. We have a net plus 2. 5 electrons to the reactant side. Okay. Here's the deal. When you guys get to that step right there, if the electrons that have been added on each of the half reactions have to be on opposite sides. If they're on the same side, you screwed up. I'm just trying to give you different ways of finding out that you screwed up before you get too deep into the thing. And again, I emphasize where you guys will have a tendency to screw up, if you're going to, is by not writing down the charges on the ions. If you don't do that, you're not going to get it to work out. Anyway, at this point in time, we've balanced each half reaction separately. Remember, what's the whole point of a redox reaction? To balance the electron transfer. Can you kind of see the similarity between the other? What's the net number of electrons it's going to have to be transferred? Or, sorry about that. What are we going to have to do to equalize that transfer? Which process is going to happen more than once? This one's going to have to happen 5 times. You see, it's very similar to the other idea. We're just doing it in 2 separate places. So now, working with both half reactions, equalize the electron transfer by multiplying the appropriate reactions, I should say, by the necessary coefficients. I should actually change that. So, as we just got done saying, this one's got to be multiplied by 5. Another place that you might make a mistake is forgetting to distribute that 5 all the way through. Now, why did we do this? So our electron transfer equalizes. At that point in time, add everything up. It does say something about canceling like species. In this particular reaction, we're not going to worry about it too much. When we get to the basic reactions, we might. So, you can do it any way you want. Gone. 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 And as usual, check that both the atoms and the net charge on each side of the equation are balanced. So I see 8 hydrogens, 1 manganese, 1 manganese, 4 oxygen, 4 oxygen, 5 iron, 5 iron. Good to go. Net charge over here is a plus 17. Over here is a what'd you get, Maisie? Plus 17. Not too bad, is it? Okay. You guys would love to do one on your own, right? Here we go. Let's just have a little fun. Let's do a different one. I want a different one. I need a book. Anybody have a chemistry book up here? Excellent. Here we go. Oh, these are too easy. I'm sorry, everyone. I'm insulting your intelligence. I'll take care of that later. All right. Ready, set, go. Okay, so we have every AP science class represented. That's cool. Freshly recreated. What happened to your paper?
I spilled water in my bed.
All right. Were you guys identifying oxidation states like that? Okay. And here's the thing, even if you screw up a little bit on that part, since we're doing the half reaction method, as long as you're identifying what oxidized, what reduced, you're still okay. All right. What did you guys start with? Oxidation or reduction? You went with oxidation?
Yeah.
Okay. So what? Sulfur oxidized? Sulfurs are done. Oxygens we need to balance by adding a water, yeah. And then the hydrogens we're going to balance by adding two, yeah. So far so good? Okay. Oh, and charge, neutral to negative, we're going to have to add 2 electrons. Yeah. Hunky dory? Next. Reduction. Okay. Manganeses are good. Therefore we need 4 water. 8 hydrogen, and 7 to 5 electrons over here. Once again, we have to equalize electron transfer by multiplying by coefficients. The top one we're going to have to multiply by 5. And this one by 2. And again, about the only place you can screw this up now is forgetting to distribute through. But add everything up. So the electrons are gone on purpose. So now we get 5 SO3s, sulfide ions, 5 sulfate ions. Whoa. How many water molecules? This is the first time we've run into this. Well, we have 5 in the top reaction. We have 8 in the bottom reaction, but they're on opposite sides of the equations, right? So what's the net number of water molecules? 3 on the product side. Everyone, that's the first time we've run into that, I believe, yes? Today. We have 16, oh no, hydrogen. 16 on the reactant side, 10 on the product side for a net of 6 on the reactant side. We have 2 permanganates and 2 manganese 2 ions. Theoretically, we're done. Always a good point to check your atoms. 2 manganese, 2 manganese. 8 plus 15 is 23 oxygens. We have 23 oxygens. 6 hydrogens, 6 hydrogens, 5 sulfur, 5 sulfur. And then just looking at net charge, 10, 12, minus 6 on this side. And over here we have 10, 4, minus 6. We pretty good? Very good. Guess what's next? Basic solution. Now you can do basic solutions with oxidation states also. You'll figure that out once we go through this. All right, so let's try a basic. So basically, no, just kidding. It's just like the acidic. Chromium oxide, I believe. Nope. I lied. The NO is a gas. Okay, here's what I would like you to do to show you how similar it is to the acidic solution. Balance both sides, both the oxidation half and the reduction half, as if it were in acidic solution, but stop when you get to the addition of the hydrogen ion. So what is that? Step like 3, I think, right? Yes. Yeah, you're doing the water, then the hydrogen ion. Okay. Don't go further than the hydrogen ion. So balance both halves of the reaction as if it were in acidic solution, but stop after you have balanced the hydrogen. Don't go any further. Do the half reaction, right. We're doing it, this is the half reaction method in basic solution. So again, you're balancing each half of the reaction as if it were in acidic solution, but stop at the addition of hydrogen. Oh, what was that guy's name? I'm going to have to look it up. I was right. It's good to know you're right. Coleridge. Yeah. It's the guy I was thinking of. Samuel. every time we do basic solutions, I think of a poem in particular by this person. You're going to hear it here in a second. All right, first of all, sign oxidation states, let me see, what do we get here? Plus 6 each, minus 2 each, minus 2, plus 2, plus 3, minus 2 each, plus 5. Everyone hunky-dory with that? I'm telling you what, right now, dichromate ion, permanganate ion, you guys are going to get really, really good at. So, what do you want to do? Or what did you do? Oxidation? Okay. Boring. Okay, so let me see. The nitrogen, nitrogen oxidized. So, NO3. Add 2 waters. Add 4 hydrogen. Hunky-dory? I put base up there. Dichromate. Chromium. Oh, this is the first time we've run into this. Oh, look. We had some people who didn't do it. Okay, so anyway, so that's the first time we've had to do that. 7 water, 14 hydrogen. And I told you to stop at that point, correct? Now, here's why we stopped at that point. Acid. Okay? You can't have a reaction that's got a bunch of base floating around and still have some acid in it. You know what I'm saying? So what we have to do is we have to neutralize that acid. What can we neutralize acid with? Hydroxide ion. So here's the only difference between the two types of solutions. In acidic solution, we leave it there, finish it off. In basic solution, we add enough hydroxide ion to neutralize the hydrogen ion that's present. So here, we're going to have to add 14 hydroxide ions. And just like your handy-dandy 7th grade math class, whatever you add to one side, you have to add to the other. So I need to add 14 hydroxide ions. Well, actually, it's time out. What you do is this. Yeah, we're good. But now what? Yeah, we just created. Oh, wow. We're not done yet. You have to do electrons. So, let me follow along here. So what do we have? Oh, I erased the negative charge here. We have a net of 2 negatives, 6 positives, so how many to this side? And up here we have 15 negatives, 4 positives. So, wait a minute. So I did something weird here. Wait a minute. Hold on. Yeah, I don't know why I did that. We have to neutralize that also. My bad, I put too many, way too many. So 4 hydroxides there. What's that? Oh, timeout. Guess what? If they're here, they also have to be, my bad. Yep, my bad. I forgot to add it to both. I said to do that, didn't I? Yeah. Except I didn't do it. My bad. I was right. And whatever we add there, we have to add over here. My bad. I got ahead of myself. I think I just went to the wrong, I went to the different reaction. My fault on that. I added the 14, I just didn't add it to the right reaction. I added it to the wrong one. So, if I'm adding 14 hydroxides, I also have to add it over here. Same thing with the 4 and the 4. This is where it starts getting a little ugly. Okay? Say hi to Dad for me, Sydney. What? That's what I'm saying. Why? Even Aaron's not on his phone. Don't do that anymore. Unless I say, hey, look this up. They'll live. They really will. I unplugged my phone too. That way nobody can interrupt us. Boggles me. All right. Now we add our electrons. So, 6, 14. We have 8 negative charges over here. We have 2 negative charges over here. So we need 6 electrons over here, right? Over here we need to add 3 electrons to the product side. Therefore, we're going to have to multiply this top reaction by 2. Ready, set, go. I will give you this hint. What did we just create right here? 14 waters. I would recommend doing something like this. What did we do over here? Created 4 waters. Hence the poem by Mr. Coleridge, Rhyme of the Ancient Mariner. Water, water everywhere, but not a drop to drink. You guys never heard that? You heard that one? We got water everywhere. You need to, and here's where some of you are going to come up with what you're not supposed to do. You need to come up with a net number of water molecules. It's going to show up on one side of the equation. This is not calculus class, where you can just leave things wherever you want them. Okay? You have to come up with a net number of water molecules. It's going to show up one time on one side of the equation or the other. A lot of times on an AP exam, what they'll do when they'll give you a redox equation to balance, they're not going to have you, they're technically not going to have you balance the whole reaction. They'll just say, what's the coefficient in front of, and they'll pick a species. Well, if it's water that they ask you for the coefficient of, and you're not coming up with a net number of waters, then obviously you're not going to get that right. Does anyone have at least which side the waters should end up on? What do you got? The product side, how many? I hear a 7. I hear a 3. I see it's 3 on the reactant side. You said the left side. Who did I talk to? You, reactant side. I got 3 when I did it. Does everything balance now? Well, I see 6 hydrogen, 3, 10, 12 oxygen, 6, 12 oxygen, 2 chromium, 2 chromium, 2 nitrogen, 2 nitrogen. Net charge of -2, net charge of -2. And there you go. I don't know if I would classify either of these as hard. I would classify them as, well, tedious, one, but you can't screw it up unless you skip steps. Okay? You can't screw it up unless you skip steps. Questions? We have tomorrow double period too. By golly, it's time to get another lab going. All right. Well, that's all, folks.